Fogarty. I'm a senior from Greenwich High School, and I'd like to start by thanking the Connecticut JSHS for the opportunity to present my research regarding the rapid visual detection of Benadryl cocktails via competitive amine-responsive fluorophores. Sorry, it's not changing the slideshow. Sorry.
If you're using a second screen, try using your mouse on the actual PowerPoint slide, and then you should be able to change forward.
Oh, there we go. Every 68 seconds, someone is sexually assaulted in the United States. In other words, by the end of this presentation, there will be 12 more lives forever changed physically, psychologically, and emotionally as a result of sexual violence. Oftentimes, assaulters will use the assistance of narcotics like GHB and Rofinol in order to engage in drug-facilitated sexual assault. However, these drugs have been outlawed in the United States, forcing assaulters to turn to over-the-counter alternatives, including diphenylhydramine, commonly known as Benadryl. And while current date rape detection kits exist on the market today, none that I found are able to test for DPH, and many have been pulled from the market for producing inconclusive results. As I mentioned before, diphenylhydramine is an antihistamine commonly found in over-the-counter medications. As a result of the functional group in the DPH, it induces sedative effects, especially when mixed with alcoholic beverages known as a Benadryl cocktail, including drowsiness, amnesia, and blackouts. As such, there is a dire need for a portable, rapid, and simple diagnostic system for the detection of diphenylhydramine in the presence of Benadryl cocktails. I intended to create this with a color shift from a red to a green sensor to indicate a safe versus unsafe beverage using a competitive 2-dye system of fluorescein isothiocyanate and protoporphyrin 9. The inspiration from this project came from a paper by Ru and Angia, who used similar amine-based sensors for the detection of fish freshness in a gaseous sensor. This jump-started my research into similar dyes for the detection of diphenylhydramine in alcoholic beverages. Fluorescein isothiocyanate was used as purchased from Sigma Aldrich and then dissolved in 10 milliliters of ethanol in order to find the optimal excitation and emission spectra. As you can see in the figure to the left, the x-axis indicates the wavelength in nanometers and the y-axis indicates the fluorescence intensity. You can see that at 475 nanometers excitation, the FITC produces a maximum emission at 540 nanometers. Following this, the ATR FTIR of the FITC was taken to serve as a spectral fingerprint for future reference, and that is shown on the figure to the right, with the x-axis showing the wave numbers in centimeters and the y-axis showing the percent transmission. PPIX was then purchased from Sigma Aldrich as well. However, this was prepared with DMSO, toluene, and cellulose acetate in order to provide a filter paper friendly substrate. Similar to the FITC, the analytical characterization of the CAPPIX was found with the same excitation and emission spectra being taken, a 405 nanometer excitation providing a maximum emission at 620 nanometers. And similar to the FITC, the ATR FTIR spectra was taken as shown in the figure to the right, which demonstrates the successful linkage between the cellulose acetate and the CAPPIX and the PPIX. The two dyes were then combined in a 1-to-1 mass ratio, and a 3D emission scan was taken to find the overlapping excitation and emissions, ranging from 395 to 495 nanometers. After closer examination, as highlighted by the red box, we see these overlapping. And then I took the emissions, I took the spectra at 405, 410, and 425 nanometers and determined that 410 nanometer excitation was optimal as it provided the most balanced illumination of the two dyes. As I mentioned before, the sensor functions using a 2-dye system, with one dye, fluorescein isothiocyanate, being selectively conjugated to the tertiary amine DPH. We see this molecular structure in the two figures shown here. The left shows the DPH FITC conjugation being characterized by the loss of the carbon-nitrogen double bond in favor of a gain of a carbon-nitrogen single bond, as shown in the figure to the right. Spectral evidence of this was then provided, as you can see here, with the carbon-nitrogen double bond loss being shown at 1596 centimeters versus the gain in the carbon-nitrogen single bond being characterized by the peak at 1185 centimeters. Visually, this appears as the notable quenching of the FITC green dye. Once again, for practical use, this would have to be applicable in solution. So I used a well plate reader to determine spectral evidence of the FITC DPH quenching conjugate in 3 different conditions seen here. In the image to the far left, you see the dye on its own. In the image in the center, you see the dye mixture as well as the addition of water non-contaminated with DPH, and there is a slight increase attributed to the increase in volume as a result of the addition of water. However, in the image to the far right, you are seeing the spectral evidence for the DPH FITC quenching conjugate, notably that the FITC green emission is massively quenched after the addition of the DPH, whereas the PPIX remains relatively unchanged. This would establish the basis for the 2-dye system, which I would take into consideration when fabricating the sensor. In this, you're seeing that 0.7 grams of each dye was added in 10 milliliters of ethanol, which was then added onto a cellulose-based filter paper with a plastic waterproof backing. And as mentioned prior, the PPIX was synthesized with cellulose acetate. This means it is tightly bound to the filter paper because of the similar structures. Conversely, the FITC was not conjugated with, the FITC was not synthesized with cellulose acetate, allowing it to lift freely off of the paper once the beverage is added. We're seeing this reaction in practice in this diagram seen here, with 2 drops of a DPH-free beverage allowing the FITC in its liquid form to rise above the PPIX, allowing the sensor to visually fluoresce as green. Conversely, when the beverage has been contaminated with the DPH, the DPH FITC quenching conjugate is enacted, visually making the green dye essentially disappear, allowing the PPIX to continue to fluoresce and allow the sensor to visually appear as a bright red color. Spectral evidence of this filter paper was shown here with the luminescence spectroscopy. We can see once again that when 2 drops of the DPH-free beverage is added, the green dye overwhelms the red, as demonstrated by the increase in green dye emission. And we can see what visually this appears as to the reader with the central dot in figure C, and conversely with the DPH contaminated beverage, the DPH FITC quenching conjugate is once again enacted, leading to a drop in the emission, allowing the sensor to continue to fluoresce red as shown in the far right image in figure C. Now, in engineering this sensor, I decided to opt for a 2-dye color system as opposed to lateral flow technology, which we're often seeing today in pregnancy and COVID tests. Now, in short, these tests function using the movement of liquid and are dependent on the mixing of reagents in order to activate a test and a control line. However, a lot of these testing kits have issues with confusion between the test and the control line, along with flow issues, which can lead to inconclusive results due to faint lines or false test results. As an alternative to this, the color system is fully stationary, preventing those flow issues, while also having a more simple to understand just simply red to green color shift as you're seeing here. It's very visible and there's not the same issues with faint lines or inconclusive results that are common in lateral flow technology. When I was initially testing, I was worried about the issues with interferences, as cocktails typically have a variety of additives ranging in content and color and pH. And when I was initially testing, I was finding that a lot of additives, including lemon juice and wine, were producing false positive, meaning they were claiming that DPH was contaminated in the beverage when in reality there was not. After further research, I found in a paper by Angelina that discovered peptide linkages, specifically that the protonation in acidic conditions was leading to a change in shape of the functional group. And applying this to my research, I found that the protonation was leading to a change in shape of the FITC green fluorescence. As such, it was affecting the fluorescent properties, not allowing it to fluoresce even without the DPH FITC quenching conjugate. As you're seeing here, this would lead to a variety of false positives, false positives in the top image. Whereas H2O and gin, which have relatively high pHs of 7 and 6, as you're seeing, were unaffected the sensors. The later additives, including orange juice, lemon juice, white and red wine, all of which had pHs under 4, was leading to protonation of the FITC, thus preventing it from fluorescing. To remedy this, I used the 6.2 pH indicator methyl red, as well as the NaOH weak base, in order to neutralize the beverages before the placement onto the sensor. And as you're seeing in the bottom image, this fixed the issue with accurate sensors post this adjustment, showing all true negatives, indicating successfully indicating that the sensor is stable in a variety of pHs despite the original contents of the beverage. Thank you. In its final design of use, the testing kit includes an empty bottle, the methyl red indicator, as well as the NaOH weak base, as well as a very small cardboard foldable box with a 410 nanometer light filter to be used with a smartphone to capture the sensor in optimal lighting conditions. In conclusion, the dual fluorescent dye system of fluorescein isothiocyanate and cellulose acetate protoporphyrin 9 has been created with a red to green color shift to indicate a safe beverage. However, the sensor remains red if the beverage has 250 parts per million or under of DPH contamination. In its final design of use, I'd estimate the cost to be about $12 for the initial kit and $1 per test. The sensor has shown promise beyond just applications to DPH, most notably able to detect the presence of pyrrole, which is an amine as discovered by Brian Graves, which analyzed the contents and concentrations of different substances within marijuana versus tobacco smoke. It was found that pyrrole was present in the breath of marijuana users, however absent from that of cigarette users, providing essential evidence for the extension of use of my sensor for the detection of marijuana breath typically found in those driving under the influence of cannabis. With the research that's been conducted thus far, I've been able to see success as the same red to green color shift has been indicated for a pyrrole negative sensor indicating a safe driver versus the pyrrole positive sensor remaining red, indicating an unsafe driver on the roads. Future research will include continuing these trials to ensure the validity in the extension of this research. I'd like to end by once again thanking the Connecticut JSHS for the opportunity to share my research, and most importantly, my mentor and science research teacher, Mr. Andrew Bermonti, for his undying support and patience. Thank you.